Alright, so in this video we're going to derive the Laplacian in spherical coordinates in under 2 pages. And we're going to do it in a very short period of time. Normally, deriving the spherical Laplacian takes, 3 hours. And it takes like 10, 11 pages of paper. And it's just a lot of application of the chain rule. So here we're not going to go that route. We're going to do it the short way, the easy way. And we're going to use complex variables to do all the heavy lifting for us. As a side bonus, this method also gives you the Laplacian in polar coordinates and the Laplacian in cylindrical coordinates. I had a quantum mechanics exam. Very first question was to derive the Laplacian in polar coordinates. All right, so before we get started, let's review a few basic things. Remember that you can treat the xy plane as the complex plane, right? So x, y, and here's a typical point, C, in the plane. So you can either label it as x, y pair, or you can label it as a complex number. So we can call C x plus I, y, right? Nobody should have any problem with this. It's very straightforward. And we're going to copy the labels that we use over in this main primary diagram over onto this. So the angle between this line and the y-axis is going to be called phi. Just labeling, and this length between the xy origin and the point C is going to be called rho. So using that, we can call the point C, we can write the point C in the form rho e to the I phi. Nobody should have any trouble with that. If you want to know how to get that, you just substitute for x, rho times the sine of phi, substitute for y, rho times the cosine of phi, right? And you factor out the rho, and then you use the Euler's formula for e to the I phi. All right, so continuing our review of complex variables, just as preparation for the actual derivation, we're going to consider a complex valued function f in this xy plane, which we're treating as the complex plane. So it's a complex valued function on the complex plane. It's a mouthful, but that's what's going on. So we can write that as f of c, but remember it's complex valued, so there's going to be the value that f takes on when you evaluate it at c is going to be a complex value itself, right? So we can write the real part as a function of c and the imaginary part as a function of c, which we'll write as v here. Right? Nobody should have an issue with this, hopefully. But alternatively, we could write the same thing as f of xy, and we can write the real part as, again, u of xy plus I of v of xy. We're just, instead of writing a complex number, we can just write these tuples. They represent the same point in the complex plane. All right? One last bit of review. So we just said that we're going to write f, which is a complex valued function on the complex plane, in this form, u of c plus I v of c, which alternatively could be written u of x plus I y plus I times v, which is a function of x plus I y. I think I used a comma a few seconds ago. Either way, it doesn't matter. In this form, you can actually see things come out right in this form when you take partial derivatives. All right, so the thing we're going to review is derivatives. Derivatives of f. What's so special about that? Well, f is a complex valued function on the complex plane, but since we're dealing with the plane, we can take the derivatives by approaching the point C from any direction. Right? I'm sure you remember this from your multivariable calculus. I'm not sure what it's called in your school. But And they all have to be equal for the derivative of f to exist, right? So to that end, we're going to take the derivative of f at point C along the x-axis, right, along in the x direction. We're going to do that by taking a partial derivative with respect to of f with respect to x, right? So that would be partial of u, partial of x, and then use the chain rule, but the partial of x with respect to x is just 1, right? Plus I times the partial of v, partial of x, right? But then we're going to use the chain rule again, and we find 1 comes out here. Partial of x with respect to partial of x is 1, right? And the partial of y with respect to x, of course, is 0. Right, so now we're going to take the same derivative, but do it in the y direction. So it's the partial derivative of f with respect to y. So that's going to be partial of u with respect to y. Now, by the chain rule, we're going to get an I out, right? Partial of x with respect to y is 0, but the partial of iy with respect to y is just I, right? So we're going to put an I out front. Times I partial of v with respect to y. And again, we're going to use the chain rule. And we get an I out front. But these I squared means we're getting actually a negative 1 out front. I'm not going to write it that way. Nobody writes it that way. We're just going to put negative. Now, as we've already argued, these two derivatives should be equal. And for two complex numbers to be equal, their real parts have to be equal and their imaginary parts have to be equal, right? I shouldn't have lost anyone at this point. So that is to say the partial of u with respect to x must be equal to negative partial of v with respect to y, right? And the partial of v with respect to x must be equal to the partial of u with respect to y. Right? And these two equations are called the Koshi-Riemann equations, right? You should have seen this in complex analysis, if I know how to spell. The Koshi-Riemann conditions. I believe that is the last bit we need to review. So from this point on, we're going to be doing the derivation. So glad you made it this far. Pat yourself on the back. All right, so wrapping up, we need one more thing, and that is the Cauchy-Riemann conditions in polar coordinates. Right now we have it in the xy coordinates, and we just need the polar, and that will conclude this last bit of review. If you already know the Cauchy-Riemann conditions in polar and Cartesian coordinates, you might as well skip ahead. It's the polar that is a little bit harder to remember, so it's a good idea to be able to derive it. All right, so we're going to proceed just like we did before. We're going to take the derivative of f with respect to phi and the derivative of f with respect to rho, and then we're going to equate the real and imaginary parts. That's going to be the end of it, trust me. So the first step, the partial with respect to phi. So let's get into it. Partial of u with respect to phi, and the derivative, the inside with respect to phi is rho e to the I phi times I, right? The same thing with the left, the second term. So we're going to take the partial of v with respect to phi, and we'll get the exact same second factor on the end, because we're taking the same partial derivative. It'll be rho e to the I phi times I. Now, oops, there should have been an I out front already. Now we're going to combine these two i's together to form a -1. So there was an I there already, and the derivative of the argument to v yields an I, which we're going to combine together into an I squared, which gives you -1. Okay, so we're going to do the same thing, but with the derivative with respect to rho. So it's partial of u with respect to rho. We're going to use the chain rule now. We're going to get an e to the I phi out. Plus I partial of v with respect to rho. And again, e to the I phi using the chain rule. Now let's equate the real and imaginary parts. So the real part here is partial of v with respect to phi, but I'm going to write the second factor of that term out front. So rho e to the I phi, partial of v, partial phi. Is that negative? Can't miss that. That'll be equal to the real part of the second equation, which is e to the I phi, partial u, partial rho. Next, we're going to equate the imaginary parts, and that's rho e to the I phi, partial u, partial phi. So rho e to the I phi, partial u, partial phi. That'll be equal to the imaginary parts of the second equation, which is e to the I phi, partial v, partial rho. Now you may ask yourself, why aren't we canceling out these e to the I phi's? That's a good question. Let's do that now. Well, let's not erase. So let's cancel out the e to the I phi's. All right? All right, so in the end, this is what we get. We get rho partial of u with respect to rho equals partial of v with respect to phi. Is the first Cauchy-Riemann conditions for polar. And we get a second equation, which is rho to the -1, partial of u, partial phi, equals negative partial of v, partial of rho. All right, so these are Cauchy-Riemann conditions for polar. And that completes the review we need, I hope. All right, so that ends the review. At this point, we're going to start the derivation, and congratulations on reaching this point, by the way. So the first step is to write down the Cauchy-Riemann conditions for the xy coordinates. That was partial of u with respect to x is equal to the partial of v with respect to y. Right? We just did it. You should remember it. The partial of u with respect to y is equal to the negative partial of v with respect to x. Right? So those are the Cauchy-Riemann conditions we just found in the review. The first thing we're going to do is take the derivative with respect to x of the first equation. Right? So you get, u with respect to x. Wow. Let's erase that. Is equal to the second partial of v with respect to y and x. And we're going to write it in this order because we're taking the derivative with respect to y first and then x. And for the second equation, we're going to take the derivative with respect to y. So we get the second partial of u with respect to y is equal to the second partial of v with respect to x, then y. And there's a negative here. That we seem to forget. There's a negative there. So remember that. Now we're going to sum these two equations together. And we're going to get something very familiar. Partial of u with respect to x, second partial I mean, plus the second partial of u with respect to y. So u. is equal to the second partial of v right, and this is equal to 0 due to the quality of these second partials. This is typically a theorem due to Clairaut, but there's also another word for it. It's called the harmonic condition. Right, so harmonic condition. So this is step 1. Step 2, we're going to repeat the same thing, but with polar coordinates, the Riemann conditions in polar coordinates. And that'll be the bulk of the work that we need to do in order to get the Laplacian in spherical coordinates. So hold on. So we're going to repeat the same exact thing, but with the Koshi Riemann conditions in polar coordinates. And after this step, that's the big bulk of the big part of the derivation, is just finding the harmonic conditions in both polar and Cartesian coordinates. So let's start. The Koshi Riemann conditions in polar, I'll remind you, were rho partial of u with respect to rho equals partial of v with respect to phi, and the rho to the negative 1 partial of u with respect to phi equals partial of v with respect to rho. This was negative. Don't lose track of your negative signs, please. It's a real pain to backtrack. So we're going to proceed in the exact same way as we did before. Equation 1, we're going to take the partial derivative of with respect to, I believe, rho. So let's do that first. What we get, both of these are functions of rho, so we have to use the product rule, Leibniz rule, whatever you want to call it. So it's rho times the derivative of the second factor, which is rho second partial of u with respect to rho, plus, now we'll take the derivative of the first factor and leave the other factor alone. So that's just the second factor, partial of u with respect to rho. Now let's do the right-hand side. That gives us second partial of v, Jesus, with respect to rho. Right, so this should be pretty straightforward. All right, let's do equation 2. We're going to take the partial derivative of equation 2 with respect to phi. So here, the first factor does not involve phi. It's only the second factor of this left-hand side that involves phi, so things are pretty straightforward here. Right, so we get rho to the minus 1, second partial of u with respect to phi is equal to negative second partial of v partial of phi partial rho, in that order. And you should be able to see what we're about to do right away. We're going to add these two together, and it'll be equal to 0 because the right-hand sides will sum to 0 due to Clairaut, or whatever you want to call it. So that gives us rho second partial of u with respect to rho plus partial of u with respect to rho plus rho to the minus 1, second partial of u with respect to phi, and that's equal to 0. That's the harmonic condition again. Right? Alright, so the story so far is that we found the harmonic conditions in polar coordinates and in Cartesian coordinates. I'm going to write those down now, just as review. So we have partial of u, second partial of u with respect to x, plus the second partial of u with respect to y, is equal to 0. But we also saw that in polar coordinates, we have the partial derivative of u with respect to rho plus rho, partial derivative of u, second partial of u with respect to rho, plus rho to the minus 1, second partial of u with respect to phi, is equal to 0. These were our two harmonic conditions. Now before we proceed, we're going to make one modification. We're going to divide equation 2 through by rho. That means this becomes rho to the minus 2. This becomes rho to the 0. So we've divided it out. And this becomes rho to the minus 1. Right? So these are our two harmonic conditions. All right? They're both 0. And let's equate them to each other. So second partial of u with respect to x plus second partial of u with respect to y is equal to the second partial of u with respect to rho plus 1 over rho, second partial of, first partial of u, sorry, with respect to rho. I'm not sure why there's a 2 there. Interesting. Plus, finally, 1 over rho squared, second partial of u with respect to phi. So this is our first win. This is the spherical Laplacian in polar coordinates. So this just falls out from the Koshi-Riemann conditions. If you already know the Koshi-Riemann conditions, it's just a matter of taking the derivative of one equation with respect to one variable and one equation with respect to the other, and to derive those harmonic conditions and set them equal to 0. Right? So this is our first big win, and our next step will be to add the partial derivative with respect to of u with respect to z to both sides, so that we can continue on. Actually, let's do that here. So we're going to add to both sides the partial derivative, the second partial derivative of u with respect to z. Right? Second partial of u with respect to z. Here's our second big win. This is the Laplacian in cylindrical coordinates. So immediately we already have polar and cylindrical. Our last step will be to make the jump from cylindrical to spherical. So in all, this should take you 1-2 pages. So stay tuned for the last and final step. So our final push to the spherical Laplacian, we'll use the cylindrical Laplacian as the starting point. Just to refresh your memory, this was this cylindrical Laplacian. It's this second partial of u with respect to z, plus the polar Laplacian that was what we initially found. Our first step will be to replace these first two terms with something. All right. So, as you recall, the first step we took was to make the xy plane into a complex plane. Now we're going to do the very same thing, but with the with the rho z plane, which is this plane right here. You'll notice right away the similarities between these two. And because they're so similar, it's the exact same steps. So we do not have to repeat all of that work. I repeat, do not repeat all of that work. What we're going to do is, in the Laplacian we found for polar last time, every time we see an x, we're going to replace it with rho. We're just going to do a substitution. So we're going to get twice as much work for free, essentially. And every time we see a y, we're going to replace it with z. every time we see a phi, we're going to replace it with theta. Oh, why am I putting equal? Every time we see a phi, we're going to replace it with theta, and every time we see a rho in that equation, we're going to replace it with r. So what does that look like after you've made the replacement? Hopefully you still have the original equation up because I'm tired of writing. So every time we see x, we put a rho, right? So second partial of u with respect to, instead of x, we're going to put rho, plus the second partial of u, instead of y, we're going to put z, right? That'll be now equal to the second partial of u with respect to, let's see, it was rho squared in the old one, so it'll be r squared in this one. Plus, instead of 1 over rho, it'll be 1 over r. Remember, we're making that replacement. Second partial of, first partial of u with respect to, instead of rho, it's r. Plus 1 over r squared. Instead of phi, we're using theta. So second partial of u with respect to theta. All right, so now that we've completed that essentially free step, we know we can substitute these two terms for what we just found, right? Which was in terms of r, rho, z, and theta, right? Making that substitution, we get the following. So we substitute these first two terms for what we just found just a second ago. That's partial of u, second partial of u with respect to r, plus 1 over r, partial of u with respect to r, plus 1 over r squared, second partial of u with respect to theta squared, right? So this is the same thing as above. Now we're going to just add on the rest. 1 over rho, partial of u, partial of rho, plus 1 over rho squared, second partial of u with respect to phi. And we're so close at this point, we just need to make a few substitutions. So in particular, we want to replace rho with something because our spherical coordinates need to be in r, theta, and phi. So we need to replace rho, and we need to replace the derivatives of u with respect to rho with something, right? And that'll be the last step, and we will be at the spherical Laplacian at that point. So these are the things we need to replace and to find. So let's get into it. Rho, as you recall, is just r sine theta. Now you should be smiling at this point and substituting mentally into your head really quick. Could that really be all that we need to do? The answer is no. We still have a little bit more work to do in terms of these derivatives. To get these derivatives, you'll need two other facts, that r squared equals z squared plus rho squared, right? You also need, let's write it down. Rho divided by z is equal to tangent of theta, right? So our last bit of work will involve finding these two derivatives, the partial of u with respect to rho and the second partial of u with respect to rho squared. And that'll be it. We'll substitute it in and recombine things and we'll be done. So just finding those last two derivatives is all we have left. So we're working on partial of u with respect to rho. And to do this, we recall that rho is a function of r and it's a function of theta. So we can rewrite this as partial of u with respect to r, partial r with respect to rho, plus partial of u with respect to theta, partial theta with respect to rho. So we have to find these two new partial derivatives. The partial of r with respect to rho and the partial of theta with respect to rho. It's pretty easy to do. Let's start with partial of r with respect to rho. To do that, we're going to do implicit differentiation. So we're going to differentiate equation 2 here with respect to rho. So what we get is 2r, partial r with respect to rho. Z is equals 2 rho, partial of rho with respect to rho, which is 1. All right? So that means that partial of r with respect to rho is equal to rho divided by r, right? Which is equal to, I believe, sine of theta. Because rho is equal to r sine theta, and if you divide through by r, you get sine of theta. Right? So we have the first one. Let's move on to the second one, which is partial of theta with respect to rho. Right? Again, we're going to use implicit differentiation, and I believe we're going to use the last equation. So let's do the first side. That's 1 over z is equal to, getting sloppy here, secant squared of theta d theta d rho. Rho. So secant squared is 1 over cosine squared. So we can move that to the other side, which gives us cosine squared theta over z equals partial of theta with respect to rho. Right? Right. But we also know that z is equal to r cosine theta. Right? So we lose cosine theta. Well, let's not be lazy here. So we get cosine squared theta over r cosine theta. It cancels one of the thetas, so you get cosine of theta over r. And that's our next derivative. All right, so the final result for this partial is partial of u with respect to r, right? And partial of r with respect to rho, and partial of r with respect to rho was sine theta, right? Plus partial of u with respect to theta, and partial of theta with respect to rho, which was cosine theta over r. Not too bad. So we're finally at the end. We have the last two pieces we need. We know that rho is r sine of theta. And we know that the partial of u with respect to rho is equal to the partial of u with respect to r, partial of r with respect to rho, which is sine theta, and the partial of u with respect to theta times our cosine theta over r. So those were the last two pieces we needed, right? We needed to replace this theta, and we needed to replace this first derivative of u with respect to rho. I mistakenly said that we needed the second partial of u with respect to rho, but that was replaced in an earlier step. So these are our last two pieces. So our job now is to substitute them in. Right, and the first thing we're going to do is, well, let's do them both simultaneously. Let's substitute them both simultaneously into this equation. And then we're going to rearrange and make it look pretty, okay? So partial of u second partial of u with respect to r, plus 1 over r, second partial of u with respect to r, plus 1 over r squared, second partial of u with respect to theta squared. I have a feeling I'm going to run out of space. 1 over r sine theta, partial of u with respect to rho, which was this monster here. And then we have 1 over r squared sine squared theta from this term, and then the second partial of u with respect to phi. Right, so this doesn't quite look like the spherical Laplacian yet. There's a little bit of rearranging that still has to be done. And let's look at that now. All right, so the first thing we're going to do is to combine all the partial derivatives with respect to r. So we have this guy here, we have this guy here, and we have this guy here. So when you bring this term out of this bracket, the signs will cancel, which gives you 1 over r partial of u with respect to r, which is identical to this guy. So what we have is partial of u, second partial of u with respect to r, but 2 of these 1 over r's partial of u with respect to r. All right, so next we're going to combine all the theta terms together. All the partial derivatives of theta together, I should say. That gives us 1 over r squared, second partial of u with respect to theta. And we have another term, which is right here. That will be cosine theta over sine theta, and 1 over r squared, right? So cos theta r squared sine theta, partial of u with respect to theta. And those are all our theta containing partial derivative terms. And lastly, we'll find the terms that contain phi, right? Which terms contain phi? That's this last term. It's 1 over r squared sine squared theta, partial of u, second partial of u with respect to phi. Right, so this looks closer, but we're not quite there yet. To get there, we're going to have to employ a few tricks. So our first trick is to combine these first two terms together using exploiting the chain rule, the product rule, I should say. So we're going to write partial with respect to r of r squared partial of u with respect to r. Now that gives us 2r partial of u with respect to r which is not quite what we have here. So to get to there, we need to divide by 1 over r squared. So instead of 2r, we get 2 over r partial of u r. Right, and the next term we'll have the r squared and then the second partial. So that r squared will cancel, so it'll give us this term. So just do it, see that it works. But really what we exploiting is the Leibniz rule, the product rule. All right, so for the second two terms, we can exploit the same thing. We're going to exploit the product rule again. This time we're going to do partial of theta with respect to theta. One of the factors will be this partial of u, of course, with respect to theta, so that we can get this, so that we can get that out. Let's see. So if we look, we see that there is a cosine here, so derivative of sine would give us that cosine. So let's try that first. So derivative of sine of theta will give us the cosine. But we don't have a sine here. So we're going to have to divide that sine out. And we do have an r squared in both, so let's factor that out. I believe this is right, and you just check. So both forms are the spherical Laplacian. It's just you have to use the product rule to combine these two terms, right? And our last step is just to reproduce. There's nothing to combine in the last step. It's just that. All right, so this is the Laplacian. It was super easy to get the polar, and the cylindrical followed right after that just by adding a second partial of u with respect to z. Making the switch from the cylindrical to polar involved duplicating our work that we did before, but that was just accomplished by substitution. And after that substitution, we had to find two things: the rho and the second partial of u, and the first partial of u with respect to rho. Find two things and substitute them in, combine them down, and do a final simplification using Leibniz rule, product rule. That's it. Hope you enjoyed.